Dear everyone, in today's video lecture, we'll be learning about infrared spectroscopy under the course of pharmaceutical analysis. So let's start. Infrared spectroscopy is a type of absorption spectroscopy that deals with the infrared region of the electromagnetic spectrum. Infrared radiation, which extends from zero point 0.8 to 200 micrometer, affects only the vibrational and rotational energy level. So, other than the UV spectrometry, the main difference between UV and infrared spectroscopy is that UV has higher strength and higher frequency or higher energy than that of infrared spectroscopy or infrared radiation. Okay, so UV can cause some electronic transition also, but infrared spectroscopy or infrared ray is not that much more strong enough as UV. That's why it affects only the vibrational and rotational energy level. So this is the electromagnetic radiation spectrum. You can see the higher energy is X-ray, ultraviolet, then our sunlight, then infrared, then microwave, radio wave. Okay, the infrared region is subdivided into three parts like near IR. The NIR extend from zero point 0.8 to 2.5 micron. It is concerned with low energy electronic transitions as well as vibrational and rotational changes. Then infrared region extend from 2.5 to 16 micron. Frequency is 4000 to 625 per centimeter. It affects only the vibrational and rotational energy level. Then far infrared region, that is FIR, it extend from 16 to 200 micron. It affects only the rotational energy level of the molecule. The absorption of infrared radiation can be expressed either in terms of wavelength or wave number. Mostly infrared spectra of organic compounds are plotted as percentage of transmittance against wave number. So let's discuss the theory of infrared absorption. Basically, its theory is as those of UV or fluorometry. You already know that in spectrophotometry or spectrophotometry, compounds receive some radiation, and after that it absorbs some radiation, and some of them are transmitted. And by utilizing the transmitted energy, we usually measure the nature of the solute or analyte. Okay, the energy of the molecule consists of translational, rotational, vibrational, and electronic energy. But in case of infrared absorption or infrared radiation, will only have the rotational and vibrational energy. Then that means is equal to the total of electronic energy of vibrational, energy of rotational, and energy of translational. So translational energy of a molecule is associated with the movement of the molecule as a whole. For example, in a gas, rotational energy is related to the rotation of the molecule, whereas vibrational energy is related to the vibration of atom with the molecule. Finally, electronic energy is related to the energy of the molecule's electron. Okay, so infrared ray is not uh, strong enough to cause electronic transition. Okay, so it is only applicable for UV. Okay, but for infrared radiation, rotational energy and vibrational energy is uh, happened. The IR radiation doesn't have enough energy to induce electronic transition as seen with the UV. Absorption of IR is restricted to the compounds with small energy differences in the possible vibrational and rotational states. For a molecule to absorb IR, the vibration or rotations within a molecule must cause a net change in the dipole moment of the molecule. The alternating electric field of the radiation interacts with the fluctuations in the dipole moment of the molecule. If the frequency of the radiation matches the vibrational frequency of the molecule, then radiation will be absorbed, causing a change in the amplitude of molecular vibration. So these theories is like as those of spectrometry or spectrophotometry. Sometimes they receive some energy, and by utilizing energy, it undergoes some electronic transition or rotation or vibration, whatever it is, based on the nature of the incoming radiation. So this phenomenon actually happens within the molecule. Now let's discuss molecular rotation. Rotational transition are of little use to us. Rotational level are quantized and absorption of air by gases yields line spectra. However, in liquids or solids, these lines broaden into a continuum due to the molecular collision and other interactions. Then vibration. The position of an atom in a molecule are not fixed. They are subject to a number of different vibrations. Vibrations fall into the two main categories of stretching and bending. So we'll discuss this one by one. Stretching means yes, something get stretched and their distance increased or decreased. And rotation means bending. Sorry, bending means they will bend. Okay, they will move from here to there. Okay. So stretching in this type of vibration, the distance between the two atom increases or decreases, but the atom remains in the same bond axis. So it can be of two type, like symmetric stretching and asymmetric stretching. So asymmetric stretching in this type, the movement of the atom with respect to a particular atom in a molecule is in the same plane. And asymmetric stretching in this type, one of the atom moves toward the central atom while the other moves away from the it. So you can see asymmetric means both of them would be similar, either out of the direction or towards the direction. But in case of asymmetric, you can say the direction is not similar. Then bending. In this type of vibration, the position of the atom changes with respect to the original bond axis. More energy is required to stretch a spring that than the trigger to bend it. Stretching assertion of a bond appear as high frequency or high energy as compared to the bending assertion of the same bond. So bending can be of four types, like rocking, scissoring, wagging, and twisting. Okay, rocking is like a rocking chair. Okay, movement of the atom takes place in the same direction. You will see this in the next slides. Then scissoring, it's like a scissor. Okay, two atoms move toward and away from each other. Okay, like a scissor. Then wagging, two atoms move up and below the plane with respect to the central atom. And twisting, DNA double helix is a twist pair. One of them atom moves up of the plane while the other moves down the plane with respect to the central atom. The scissoring is like a scissor. Then rocking, like rocking chair. Then wagging, yes, it's also in the same plane. Then twisting, twisting means one in the one direction and another is in the totally opposite direction. Then here is some calculations regarding the stretching frequencies using the Hooke's law. Yes, whenever will give you some like ch, okay, or whenever will give you some bond, then you can easily measure the stretching frequencies by utilizing this formula. So in this formula, uh, c is the velocity of the light, k is the force constant, okay, nu bar is the frequency in centimeter, then mu is the and this calculation. So by utilizing this, we usually get this. Okay, so just go through the math, you can easily perform this problem. Just go through this, these are very easy, you can easily understand any stretching frequency of any of bond like ch, co, nh, no, whatever it is. Then now we'll discuss different vibration, fundamental vibration or overtone or Fermi resonance, lot of things regarding the FTIR. The vibration which responds to five vibrational transition is called fundamental vibration. Okay, fundamental means very basic. The zeroth vibrational level of the first vibrational level on absorption of IR radiation is called fundamental vibration. Then overtone, any multiple of fundamental vibration on absorption of IR radiation is called overtone. So first overtone, second overtone. So vibration which occurs from zeroth vibrational level to the second vibrational level on absorption of IR radiation is called the first overtone, and second overtone is the vibration which occurs from the zeroth vibrational level to the third vibrational level on absorption of IR radiation is called second overtone. So let's discuss the instrumentation of FTIR machine. This instrumentation is as like as those of spectrometry and spectrophlorometry. Um, it can be of two type, like dispersive IR and FTIR. So here are the instrument. This instrument is as like as those of spectrophlorometry. which contains radiation source, sample compartment, monochromator, and detector recorder. So radiation source is the basic source of the IR radiation. Then sample compartment, where compounds or the samples is kept after prepared after preparation. Then monochromator, its function is, as the name suggests, mono means single and chromator means light. Okay, that means it converts any multi-directional light into a single directional light. Okay, then detector, it will detect the radiation or transmitted radiation, and from this it will get the result in the recorder. So let's discuss this compound one by one. Here is the basic uh, instrumentation of FTIR. So let's discuss one by one. First of all, radiation source. An inert solid is electrically heated to atmosphere in the range of 1500 to 2000. The heated material would then emit infrared radiation. Then sample compartment. After preparation of sample, it is inserted into holder and then placed in the sample compartment in the path of IR beam. For solutions, a reference cell is needed that contains solvent only. After passing through the sample and reference, the beams are topped by mirror which focuses each beam alternately into entrance slit of the monochromator. Glass and plastic absorb strongly throughout the IR region of the spectrum. The cells are constructed by ionic substances like sodium bromide and potassium bromide. This is the uh, sample compartment. Then monochromator, a monochromator selects specific frequency from other extraneous radiation using either a prism or a diffracting gratings. Then detector, the detector senses the differences and determine which frequencies have been absorbed by the sample and which frequencies remain unaffected, and send signal which is amplified by the amplifier. And finally, the recorder. The amplified detector signals is recorded as percent of transmitted light versus frequency on a chart. So this is the instrumentation. So now we'll see the sample preparation. Okay, this is one of the critical stage for FTIR, because sample preparation is not as like as those of UV spectrometry or any other fluorometry or atomic absorption spectroscopy, whatever it is. Its sample preparation is much more different from that of other spectrometry or chromatography. So let's discuss one by one. IR spectra may be obtained from all phases, solid, liquid, and gaseous. So the vapor or a gas is introduced into a special cell, usually about 10 centimeter long, which is then placed directly in the path of one of the infrared beam. The end wall of the cell are usually made of sodium chloride, which is transparent to infrared from 4000 to 650 per centimeter. Then liquids. The liquids are usually examined as thin film sandwiched between two polished salt plates made of NaCl and potassium bromide. The pair of plates is inserted in a holder which then placed in the path of IR beam. It is the simplest of all procedures. KBr is transparent throughout the 4000 to 400 per centimeter. This is the basic range of IR spectrometry. That's why KBr potassium bromide is used. Then solids. Three methods are commonly used for the preparation of the solid sample for measurement of ion absorption. First of all, potassium bromide disc. About 1 milligram of the sample is finely grounded with about 300 milligram of potassium bromide in a mortar. Okay, sample is mixed with potassium bromide. The mixture is pressed into disc using a special mold and hydraulic press. Under pressure, potassium bromide melts and seals the compound into a matrix and form a potassium bromide disc. The potassium bromide disc can be inserted into a holder which is then placed in the spectrophotometer. Then you can see here the sample is mixed up with potassium bromide, then pressed using the special mold and hydraulic pressure, then inserted into the holder and placed in the IR path. Then IR spectrum is being taken. So this is the instrumentation of sample compartment. Then another way of applying solid is as nozzle mold in the form of suspension. About 1 milligram of sample is finally grounded in a mortar with a drop of nozzle mole. The mole is then placed between flat plates of sodium chloride. Some common molding agents like nozzle, hexachlorobutadiene, chlorofluorocarbon oil. Nozzle is a mixture of liquid paraffin hydrocarbon with high molecular weight. Then in solution, the compounds is dissolved to give a 15% solution in calcium chloride, calcium tetrachloride or uh, chloroform. The solution is introduced into a special sodium chloride cell. A second cell of the equal thickness but containing pure solvent is placed in the path of the other beam of the spectrometer in the order to cancel the solvent absorption. Okay, this is just a reference. For aqueous solution, special calcium fluoride cells are used. This is the overall method for sample preparation. You can see here. Now let's discuss the application of FTIR. So first application is identification of functional group and structure elucidation. So this is one of the core spectrometry or spectroscopy for determining or identifying the functional group or determining in a compound. By using the UV spectrometry or fluorescence, you can easily measure the concentration of the sample. Okay, but you cannot identify the sample. Again, by using atomic absorption spectroscopy, you just measure any concentration or presence of any metal or sample. Okay, but you cannot identify any functional group. Okay, so you can easily understand that IR has become very common for identification of functional group or the compound. The entire IR region is divided into group frequency region and fingerprint region. Range of group frequency is 4000 to 1500 per centimeter, while that of fingerprint region is 1500 to 400 centimeter. In group frequency region, the peak corresponding to different functional groups can be observed. According to the corresponding peaks, functional group can be determined. Then identification of the substance. Iris spectroscopy is used to establish whether a given sample of an organic substance is identical with another or not. This is because large number of absorption bands is observed in the IR spectra of organic molecule and probability that any two compounds will produce identical spectra in almost zero. So if two compounds have identical IR spectra, then both of them must be samples of the same substance. The IR spectra of true enantiometric compound are identical, so IR spectroscopy fails to distinguish between enantiomers. Then studying the progress of any reaction. Progress of chemical reaction can be determined by examining the small portion of the reaction mixture withdrawn from time to time. The rate of the disappearance of a characteristic absorption band of the reactant group and the rate of appearance of the characteristic absorption band of the product group due to formation of product is observed. So by this you can easily understand the progression of any chemical reaction. And finally, the detection of impurities. IR spectrum of the test sample to be determined is compared with the standard compound. If any additional peaks are observed in the IR spectrum, then it is due to the impurities present in the compound. Now we'll see different factors which affect the vibrational frequencies. First of all, electronic effect. So changes in the absorption frequencies of a particular group takes place when the substituent in the neighbor group of the particular group is changed. The frequency shift are due to electronic effects which change the force constant of the bond strength, resulting in the change of absorption frequency from the normal value. The absorption of carbonyl group in the following compounds are different. So you can easily see the electronic effect. So here is acid chloride, here is ester, here is aldehyde, here is ketone, here is carboxylic acid, amide, and acid anhydride. You can see the RCO is common. RCO is common for all, but the main difference is the uh, their functional group. Like here is Cl, here is OR, here is only H, here is R, here is hydroxyl, here is NH2. Okay, the RCO is common, but for different electronic effect, their uh, their stretching frequency is much more different. Okay, you can see it has been decreased dramatically. So the main thing is if you use electron donating, then its value would decrease. Okay, this is electron donating agent. Okay, these are very good agent, functional group. They are electron donor, and their frequency would decrease. Then if you use electron withdrawing group like Cl or OR, these are electron withdrawing group, then obviously their frequency would be higher. Then for resonance, the frequency would get decreased. For S bonding, the frequency would get decreased. Then coupled vibration and Fermi resonance. We expect one stretching absorption frequency for an isolated CH bond, but in case of methylene group, two absorption occurs which correspond to symmetric and asymmetric vibration as follows. In such cases, asymmetric vibration always occur at higher wave number compared to symmetric vibrations. These are called coupled vibrations because these vibrations always occur at different frequencies than that occurred for the isolated CH stretching. Sometimes it happens that two different vibrational levels have nearly the same energy. If such vibrations belong to the same species, then mutual perturbation of the energy may occur, resulting in the shift of the one towards the lower frequency and the another towards higher frequency. This phenomenon is called Fermi resonance. So Fermi resonance means two different vibrational levels having the same energy. Then okay, sometimes you may have very bigger frequency, or sometimes you may have very diminished frequency. Okay, and this phenomenon is called Fermi resonance. Fermi resonance is observed by aldehyde in which CH stretching absorption usually appear at doublet due to the interaction between CH stretching and CH bending. Okay, CH stretching is the fundamental and bending is the overtone. Carbon dioxide shows two band at 1285 and 1388. Acetic anhydride shows two CO stretching absorption band at 1810 and 1760 per centimeter. Then hydrogen bonding. Hydrogen bonding brings about remarkable downward frequency shift. Stronger the hydrogen bond, greater is the absorption shift toward the low wave number than the normal value. Two type of hydrogen bond, intermolecular molecular and intramolecular, can be readily distinguished by IR spectrum. First of all, intermolecular is bond gives broadband absorption is concentration dependent, and absorption difference between the free and associated molecule is more than intramolecular is bond gives sharp all defined band, and absorption is concentration dependent. So you can easily understand that for the presence of hydrogen bond, usually there occurs shift of there occurs shift of the frequency, or the peak. The absorption difference between the free and associated molecule is less. In aliphatic alcohol, a sharp appear at uh, 3650 in diluted solution due to free hydroxyl group, while a broad band is noticed at 3350 centimeter due to is bond of OH group. Then bond angle, you can see here different bond angle. Okay, is bond angle is higher, then it is lower, then its bond angle is too much lower. Okay, for higher bond angle, you can see its transmittance is lower. Okay, frequency is lower. So small rings have a shift in the vibrational frequency to higher energy. Therefore, 5, 4, or 3 mm rings having the carbonyl stretching frequency shifted. Angle strain in this ring cause the carbonyl group to have more electron density, therefore a steeper bond. Okay, so there are a number of IR bonds. Just go through this. So OH and NH stretching. So both of these occurred around the 3300 centimeter per centimeter, but they look different. Alcohol OH is broad because of the OH hydrogen bond with rounded tip. Primary amine is broad with two sharp peaks. Secondary amine is broad with one sharp peaks. Why one? Because of one hydrogen bond. Why two? Because primary amine has two hydrogen bond, but no signal for tertiary amine because they don't have any hydrogen bond. Then you can see here as an example the IR spectrum of alcohol. Okay, as it is alcohol, it will contain hydroxyl. For hydroxyl, it will have 3300 per centimeter, in the range of 3300 per centimeter absorption. Then you can see the saturated CH stretch. The broad shape is due to the hydrogen bonding interaction of the alcohol molecule. Then iris spectrum of the amines. The iris spectrum of amine show a broad NH stretching absorption centered around 3300 per centimeter. So for amine, CH very sharp peak. Then NH, for NH you will have the bond here 3300 per centimeter. Then amides, for amide, CONH2. For CO, you will have a peak at 1630 or 1660 per centimeter, and for NH, you will have bond at 3300. Now, this is our final topic, like applications of IR spectroscopy. So, We have already seen that our spectroscopy can be utilized for the identification of any functional group and thereby the identification of the overall compound. Okay. um, so entire eye region is divided into group frequency region and fingerprint region. Range of group frequency is 4000 to 1350 per centimeter, while that of fingerprint region is 1350 to 400 per centimeter. So in group frequency region, the peaks corresponding to different functional groups can be observed. According to the corresponding peaks, functional group can be determined. So by this, we can easily understand the nature, or by understanding the peak or its nature, we can easily understand the availability of any functional group. Then identification of substance. Each atom of the molecule is connected by bond, and each bond requires different eye regions, so characteristic peaks are observed. It contains very complicated series of absorption that are mainly due to all manner of bending vibrations within the molecule. The region of eye spectrum is called fingerprint region. Okay, we know fingerprint region is just below 1500 per centimeter wavelength or wave number. So this region is called fingerprint region. Okay, because it contains very complicated series of absorption, and fingerprint is same for all human being, or all everyone. It's different, okay, from person to person. So this fingerprint region would be different from molecule to molecule. Identification of a compound can be revealed by comparing its fingerprint region with the spectra of the organic sample with identical condition. So here are more other peaks. So here is the spectra of ethanol. The contains hydroxyl group, so it will contain some broad hydroxyl peak at 3300 per centimeter. And for the availability of hydrogen bond, it's a broad band. Okay, so this is for aspirin. Aspirin contains hydroxyl group, then carbonyl group. Okay, for hydroxyl group, 30 in 3300 per centimeter it will have a bond. Then in also you can see here in the region of 1600, if you see it closely, this is the region of 1600. In 1600 you can also say carbonyl peak. So two carbonyl peak, two peaks. Then this is for paracetamol. This hydroxyl, obviously this will have a broad 3300 per centimeter wave number. Then for nh, it will also have the 3300 per centimeter wave number. Then for the carbonyl, it will have 1630 per centimeter wave number. Okay, so this is easily understandable by the peaks. Okay. Then finally, detection of impurities. Our spectrum of the test sample to be determined is compared with the standard compound. If any additional peaks are observed in the air spectrum, then it's due to impurities present in the compound. And finally, quantitative analysis. The quantity of the substance can be determined in pure form. Most simple quantitative infrared methods of analysis use the intensities of the carbonyl, amine, or hydroxyl. So the overall bond and the type of compound and frequency range and intensity has been shown in this table. Just go through this. So if you have any confusion, please inform me in the comment section. Thank you.